Hi, this is Jeff Coronado on behalf of JCSE, and this is Bridging the Gap. So Bridging the Gap is a series of structural engineering design tutorials that we have here in the office that we use, and I think by extension, they can be used by young structural engineers maybe who are still even in school. So if you're still in school, but you're towards the end of your education and you're trying to look for a head start, if you will, on becoming a structural engineer, as we all know, I think fair to say, there are much fewer slots in structural engineering employment opportunities than there are graduates. So I think fair to say any head start that you can get that makes you better equipped, better prepared to jump into industry, it's to your advantage. Also, young engineers in their first few years, it can be overwhelming, right? The gap that's there between what industry expects you to know and what you actually learn in school sometimes can seem pretty large. So this is all in an effort to try to bridge that gap and make things a little bit smoother for you in making that transition. So today in particular, what we're going to talk about is how to stiffen an exterior stud wall when a stair occurs. And for that matter, you can extrapolate this to a stair, from a stair to any opening that's immediately at any opening in the diaphragm that's immediately adjacent to an exterior wall. We're talking about a stud wall, so type 5 type construction. The question that came in basically was from a young engineer who said, does having a stairwell adjacent to an exterior wall create an instability? The detail in particular that we are looking at is WW6A. So if after listening to this tutorial, there still are some questions pertaining to this topic, you might want to search on our channel for WW6A, and there might be related tutorials associated with this that might kind of fill in some blanks. Otherwise, by all means, feel free if there's any terms or any concepts that we kind of briefly talk about here that you're not clear on, feel free to leave a note at the end of the tutorial letting us know, and we'll try to point you in the right direction to a tutorial that does cover the question that you had or point you in the right direction. But you might want to search for WW6A because you might find other tutorials that are kind of on topic. The other thing that I'd like to kind of bring your attention to is the standard admonition: get all you can from the tutorial. I think some young engineers kind of have the habit to kind of skip around and just look for a particular value that they want instead of like digesting the lesson, right? Instead of digesting the lesson, they just kind of pick off a value. But those engineers are really shortchanging their career. They're shortchanging their progression, because then every single time they need to kind of repeat the lesson and relearn a lesson instead of just learning it correctly from the get-go, and then that way they can just kind of take off. The idea is to arm you as structural engineers, make structural engineers out of you, not just for you to kind of blindly follow a tutorial, but then every single time you have to be listening to tutorials, right? The idea is to kind of empower you as structural engineers to learn how to think like a structural engineer, so that then you can kind of take off on your own. Okay, let's see if we can scroll down here. So here we have a plan view, all right? We've got a plan view. So let me see, this whole thing here, this whole thing is a floor, all right? So all of this is floor. All of this is floor. We do have an exterior wall across here. So there's our exterior wall. The black squiggle is our floor. Let me, right here is our stairwell. So you can see the stairs are adjacent to the exterior wall. So this is an opening in the diaphragm, right? there is an opening. In this case, it's a stair. Again, it could be anything else as long as it's a significant opening in the diaphragm. And significant is probably a ratio, if you will. It's in proportion. How big is the overall diaphragm? How big is the dimension, the length of the diaphragm in comparison to the opening? But we're talking about an opening in the diaphragm. Let me see. Can we kind of quantify this? You know what? I'll bet you we can. I would tell you this. If this dimension here is, I would say, probably greater than 4 feet, I would start looking at it. I would start considering this. Okay, now, what's the instability that we have here? What's the problem that we have here? If we look at a section, through here, all right? So we're looking at a section where we do have our floor diaphragm and our exterior wall. What we're going to end up with is something that would look like this. We're going to have a wall segment, and this can be as many floors as you want to consider. So here's, let's say, our roof. Here's a floor. Here's a floor. Okay, so why did I draw the wall? Why did I draw these wall segments? Why didn't I draw them continuously if it's just one exterior wall? Well, the reason is because the wall is built out of segments. Those are studs, right? So the stud starts and stops at the floor line. In between, there's a double top plate. That double top plate is what we would refer to in school as a hinge. It creates instability in that. So think of a simply supported beam that's supported, think of a simply supported beam that's supported here, and supported here, right? With pressure applied horizontally on that exterior wall. That pressure comes from, well, it can come from several things, but more than likely it's wind that we're trying to resist. So at the floor lines, we have hinges. We need something there to resist then the pressure. Otherwise, this becomes unstable. Again, some of this may also be covered in other tutorials, so I don't want to get too much into the instabilities of this, but we do need the floor lines to absorb and to provide that stability for the exterior wall. Okay, so now what would happen if we were to draw, if we were to look at a section through where the stairs are at, or where the opening in the diaphragm is at, and we look that way? If we have that, then in essence, what we've done, what we have there is we don't have the floor bracing the wall at that point. Well, guess what? We have an instability, right? So now, this, with pressure inward, can blow in to the structure. And it would look like this, right? That with, if we had kind of wind pressure blowing into the wall, that's what would happen. The black dashed line that I've drawn in there is to show what would happen with the wall when it has wind pressure exerted on it, what we would call positive wind pressure. That whole concept of component and cladding pressure, wind pressure, that's covered in other tutorials in Bridging the Gap. So I don't want to get too much into that. Again, just leave us a note at the end of this if you have any questions in particular on those issues, and we'll try to point you in the right direction. But without the floor there, we have an instability. So what we need to do here is we need to do something. We need to do something, do this. We need to do something there to kind of provide the strength needed to make up for the fact that the floor is not there. Okay, so again, if anything here isn't clear so far, let us know afterwards and we'll try to point you in the right direction. Wall anchoring to the floor, okay. Lateral load migrates to shear walls. So there, all we're trying to get across is that, okay, so the wall comes in here and is pushing, the wind is pushing against the wall. Let's just look at an example where the wind is going from right to left. The wind pressure, by the way, can act in both directions. You can have wind on a wall and it pushes the wall into the structure, and it can pull it away from the structure. Again, that's positive pressure, negative pressure. That's covered in another tutorial on bridging the gap. So this force pushes into the wall right now. So that means that the force is kind of going its merry little way right here, right? Ultimately, this migrates. This will migrate out here. And then if we, I might be kind of shortchanging this a little bit, but let's just say that ultimately we've got a shear wall out here and we've got a shear wall down here that goes from left to right. So this pressure will migrate into the shear wall here, and it will, I don't want to do that. And it will migrate into the shear wall that's down here. I'm going to run out of real estate here, but hopefully you get the idea, right? Eventually this comes down here and gets sucked up into the shear wall that is down here. Okay, so that's how you need to visualize the forces that are going into that wall and resolving into the diaphragm. That's why we don't worry about those forces. We've got a mechanism to resist. Shouldn't say we don't worry about them. We know what the mechanism is to get those forces from the wall through the diaphragm into the shear walls. Again, the problem is that when the wind pressure is hitting our wall, and there is no diaphragm to resist that pressure, right? That's when then we need that strong element in place of the diaphragm to kind of anchor that wall so that the wall doesn't blow in or blow out. Okay, I think with that we can move on. Let me clear this. With that, we can move on and look at kind of what that section would look like cutting through the stair, cutting through the opening in the diaphragm, and where we're adding the strong element there to make up for the loss of the diaphragm. So first I would say this. This is an old school detail, what I refer to as an old school detail. So this is more of an in-house note. For those of us here, the first person that picks up this detail should fix the things that need to be fixed that we typically fix because this is old school. So, but again, that's more of an in-house note. I'm picking this detail off from another project, so that's why it's old school. We do need to make this current. But okay, with that said, hopefully that'll happen. With that said, let's move on here and look at the different components that we have in this assembly. Excuse me. All right, so we have right here a specification of 2x6 studs. All right, maybe, I don't know, that's something that needs to be engineered. And we have to decide if those exterior walls are 2x6 or if they check out at 2x6 or not 2x6, that needs to be checked out. Kind of an important thing here is this plywood filler. Now, keep in mind, plywood, the term plywood is also old school, so this needs to be changed, right? Back in the day, we used to call this plywood. Now it's not politically correct to call it plywood, so we got to call it wood structural panel. So that's fine. You know, we can play the game and we'll change that to wood structural panel or WSP. But the point is, we need that little filler, because if you do the math of how this wall assembly looks like, where the diaphragm does occur versus where there's an opening, you'll see basically what happens is this: the double top plate, and this is the double top plate, that double top plate stays at a constant elevation throughout the entire length of the wall. The same is true for this sill plate. It stays at a constant elevation throughout the length of the wall. So that leaves, let me use magenta here. That leaves this distance between the bottom of the sill plate and the top of the double top plate as an unknown, if you will. Okay, so that means that this beam that we've got here, this beam basically has to match the depth of the floor framing, of the floor joist. Otherwise, we're going to have a problem, right? So we need to try to find a way to get that strong element to fit in this cavity, if you will. If it doesn't, well, then we need to scratch our head a little bit. But that's initially, that's the idea, that it will fit in there. But then you still have this this gap that needs to be filled in between the bottom of the sill plate and the top of that beam. So that's why we put a wood structural panel filler in there to match the floor sheathing, and that bridges that gap. Now, as far as the beam is concerned, remember that what we have here, by the way, what we have here is, let's take a look at vertically acting loads. So the load from the top stud is going to migrate right through that beam and into the stud below. So really, it's not resisting any force. Gosh, I guess you could make the argument that you might need to check crushing there, but I don't know about that. And even if we did need to check crushing, that's a matter for another tutorial. Basically, if I were doing this, I'm not going to worry about the crushing on that beam. I'm just going to assume that the loads transfer directly through from stud above to the stud below. So really what we're looking at here in terms of resisting is that wind pressure, excuse me, and again, it can go in either direction, from left to right or right to left. So let's just say we have wind pressure acting from left to right, and it pushes on this assembly, right? It's pushing on those studs. And then that force has to then be resisted by this beam. So this beam, you know what, I'm not sure if I want to make that even bigger, right? Because this is like a reaction. This isn't just, this is the reaction. The beam has to resist the reaction from the stud above, which acts, ooh, I don't want to do that. From the stud above, which acts as a simply supported beam, supported by the beam here, and the stud below, which is also acting like a simply supported beam, again, supported by this beam. So this beam absorbs the reaction from the stud above and the stud below. So this beam needs to be strong enough, it needs to be stiff enough so that it, in essence, resists the thrust created at the hinge. Remember that there's a hinge here, created by the hinge between the studs. So that hinge there. You know what, let me take that out just so that we can be kind of, I didn't mean to do that, Brian. Oh, well, I'll let that go, because really the hinge is introduced at the double top plate. So that's where our hinge is at. Okay, so I already mentioned fixing the old school aspect of this detail for the next engineer here at the office that picks this detail up. The beam sizing. So yes, the beam sizing is kind of what's critical about this detail. It's calculating those out of plane forces from the wind in order to determine the reaction that occurs at this beam, and then know what the weak axis, right? Keep that in mind. Now all of a sudden this beam is not acting about its strong axis, it's bending about its weak axis. So you're designing a beam for weak axis bending. If you need help with that, I believe there's another tutorial on bridging the gap that will help you with that. But you need to resist the pressure here in weak axis bending due to the wind component and cladding pressure. Let's see, was there anything else here that we need to cover? And I don't think so. So I think that's it for this detail. If this was helpful to you, by all means, sure would appreciate if you leave us a thumbs up. Any comments or questions that you have, or any suggestions that you might have, please feel free, by all means, leave them at the end of this tutorial, and we'll try to incorporate what you have to say. And if it was helpful to you, sure would appreciate if you were to subscribe to our channel here at JCSE. And that way you can monitor future tutorials as we bring them along and incorporate them into our library here. Okay, real good, guys.